This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon. Hope your DSO soldering is getting along well. So how many of you finished your DSO? Well done. And so if you haven't finished, we have sessions running during the exam time and after the final exam. So the final exam is our ESD. After the ESD, we will be having 1 or 2 sessions. So I will be posting all the dates this week on LMS. And I also will be scheduling an extra lecture, not examinable, on Friday. So where I will be discussing about past exam and some communication protocol like SPI, I2C. Why do you want to use I2C? What is the difference between SPI and I2C, TXRX, UART? So these things are very important as a system engineer, but they're not examinable. Again, today we almost finished the syllabus. So today's lecture, what I will do is, I skipped some sections about error in the ADC. So that I will be teaching today. Then I will be showing you debugging video. So I have released a debugging video on LMS, debugging DSO, so that you know what verb form to look at. I will show you the debugging video. And then I will also discussing about some isolation techniques. Isolation techniques means how to isolate power supplies. Then isolation ICs are available. What is the need of isolation? Again, non-examinable. So in summary, we finished all the examinable materials in the last week. So whatever I am teaching today, whatever I will be teaching next week, all are non-examinable. So the DSO debugging, so this is a video we prepared, it is available on LMS so that you know what to expect.
We're going to be taking you through various important signals and showing you what you should expect on your own boards. The first thing we're going to go through is the power supply rails. These are important and you'll need to check them first because without this nothing else will work. The first thing you're going to want to check is the USB power supply rail. You should get around 5 volts on this rail.
So please check in this order so that you are systematically checking your DSO, debugging your DSO.
The next thing you're going to want to check are the +5 and -5 outputs. You will have large test points on your boards that show this. Next, you're going to want to check the 3.3 volt signal. This comes from the DC regulator and you have a small test point on your board to check this.
See, for every board, we will be checking the power supply first. That is a procedure. If your power supply, when you check ground and +5 volt, if you see 0 means it's already shorted. So there is no point in testing the signals. So we have to, that's what we do. So when you got PCB, without mounting the components, what did you do for the first? Sorry, testing? Power. But then you haven't, how power? What power? Yeah, so when you get the PCB, when you get a bare PCB, as a system engineer, what you should be testing is you take the multimeter, connect it +5 and ground to make sure that it is not shorted before mounting the components. Otherwise, after mounting the components, you don't know whether the short was there at the beginning or you, when you soldered, it got shorted. All the power supplies ground, you have to make sure that it is isolated. Again, after mounting also, we will be doing the same test. So that's the reason we prepared this video carefully. So we will test first the power supplies, even after mounting the components.
Okay, so now we're going to go through the front end of the DSO. This is the signal path from the input all the way up to the ADC. The first thing I'm going to show you is the input protection circuit. So you can see that we're giving it a 5 volt amplitude signal and we're getting a 5 volt amplitude output. And if we were to increase the amplitude of the input signal, it clamps at 5.6 volts as expected.
See, you should be getting the clamping circuit. That's how you make sure that your clamping circuit is working. So that's the reason you can see the clipping here.
So the next point is the impedance network. And you can see this scales the signal down. After this, the signal goes to a buffer. And this does not alter the signal in any way. After this, it goes to an anti-aliasing filter. As this signal is only 100 kilohertz, the anti-aliasing filter does not scale it down at all. After this, it goes to a level shifting circuit. This level shifting circuit brings it into the range that the ADC can read. After that, the signal goes into the ADC and becomes digital data. That's the end of the front end.
Yeah, so when you mount, even you can test your front end. You don't have to wait until mounting all the components or soldering all the components. Maybe you can solder and then you can test your front end. Make sure that front end is working.
The next thing we're going to be going through is the trigger circuit. The first thing you're going to want to check on this is the output voltage of the DAC. In the GUI, when you change the trigger level, you should see...
So this is what you will be getting the GUI we will be giving. And then this is, you don't have to program or make it, we will be giving this one, the interfacing part GUI.
The voltage from the DAC increasing and decreasing. Next, you want to check the output from the comparator. You should see a square wave on the oscilloscope. And when you change the DAC level, the duty cycle of the square wave should increase and decrease.
So that's a trigger signal. So that's important. You have to change the trigger level and then check it, because if the trigger level is not working, maybe your circuit might not work in the digital part. So please follow this order.
The PLL. If the microcontroller has been properly programmed, you should see a 5 megahertz square wave coming out of the clock pin on the microcontroller. If you don't see 5 megahertz, then you need to check your fuse settings on the microprocessor. This 5 megahertz signal from the microprocessor goes into the PLL, which multiplies it up to the clock for sampling in your oscilloscope. In the GUI, you can change the multiplication rate of the PLL, and you should see different clock speeds. After the PLL, this clock signal goes into the CPLD. If your CPLD has been properly flashed, you should see the same clock output on the fast clock pin. Now we're going to check one of the control lines to make sure that everything is working. When you click capture on the GUI, you should see a single pulse on the enable pin of the microcontroller. If you don't see this, you're most likely going to want to check the UART to make sure that your computer can communicate with the microcontroller. To check the UART, put the oscilloscope probe on the TX line and click the capture button. You should see a pulse similar to this, which signals the computer talking to the microcontroller. When you check the RX pin on the computer side and click the capture button, you should see a stream of data representing the captures being sent from the oscilloscope back to the computer. Hopefully this guide helped you in debugging your DSO. If you have any questions, speak to your demonstrator, and thank you for watching.
So this video I already posted on LMS so that you can test it. So these are the major pins you should be testing. So if these waveforms are working, then almost you are through. Even if there are some issues, at least we can put some jumpers and make it correcting. So first, if you know the So when you have confidence, when you have the knowledge of DSO, then you have got confidence. If you know the block level what is happening, even if some signal is not coming, you know that which block. So when you are testing, then you should be having that block level diagram in your front. Then okay, this is the part. Okay, if you suppose you are not getting a signal, then you should know, okay, that is, you can say, oh, this block level diagram I got the issue. Then you can go back to the block level diagram and fix it. Then if your DSO is working straight away, maybe you are unlucky because you are not going to learn much. But if your DSO got some issues, then you will learn a lot. I'm not joking. It doesn't mean that you should have a lot of problems. No, but if it is straight away working, you are a little bit unlucky because you are not going to learn a lot. If you got some issues, then you will be going to each block and then you are fixing it. And even I like putting some jumpers so that you know how to solve the issues. Provided you put jumpers and if it is working, I'll be very happy because you got some issue. See, you cut the track and you put the jumper and make it working means you got very good debugging skill. Plus you know what you are doing. Yeah, so we will go back to the lecture then. Anyway, this video is available on LMS. So data conversion errors. So I'll be using some of the slides from the previous lectures so that I can connect to what I'm going to teach. But then doesn't mean that these slides are already covered in the previous lecture, so it is examinable. These slides, some of the slides which I already covered. So you should not tell that no, it is taught today. So it was in today's lecture, but it is not examinable because these things we already studied. Analog to digital converter recap, which we already studied. We know what is analog to digital converter. You have got a block in your ESD subject, especially for your DSO project, A to D converter. So in the analog digital converter, we discussed it got comparators. Analog to digital means you are converting your analog signal to a digital signal, and then we know how it is happening. From a flash ADC point of view. Flash ADC means a design where you are using comparator for designing ADC. This we have studied, and then we also studied DAC. Before studying the DAC, we studied inverting amplifier, and then we studied voltage adder, then we studied DAC, if you recall, and then this is a digital to analog converter. So then we know about ADC, we know about DAC. But then when you are dealing with ADC and DAC, you also should be knowing about some error because none of these ADCs or DAC are going to behave in the way that we expect. Because there are lots of circuits inside, there will be non-linearities, there will be errors. So we should be knowing about that. We also studied characteristics in the sense what is the resolution of ADC, what is the meaning when you are saying that 12-bit ADC, 8-bit ADC, 16-bit ADC, then we are having a very high resolution which we discussed. 16-bit ADC means 1 LSB, which is equal to in 0 to 10 volt range 0.152. If it is from minus 10 to 10 plus 10 volt, it is equal to 0.305, means double of this one. So in 0 to 10 volt input range, if you are getting 16-bit ADC, then your resolution is around 152 microvolt. That's the resolution. But then we also studied effective number of bits. So what do you mean by effective number of bits? So when you buy a high resolution ADCs, usually in the 8-bit ADC, you have got 8 outputs, 8 digital outputs, and when you read the ADC data sheet, sometimes they will say if you see effective number of bits is 8, then that is good. You are getting 8-bit and then your effective number of bits is 8. But then 8-bit I don't think there is any issue, but when you are buying maybe 16-bit ADC, then you might expect your resolution as 152 microvolt. 152 microvolt means when 152 microvolt is changing in the input, your 1 bit will be changing in the ADC. So you got an application, your application is, suppose you don't know about effective number of bits. So you haven't read any data sheet, you have an application, in the application your requirement is, you want to find out a change of 152 microvolt. Then you want to change, you want to sense that change, 152 microvolt. Then what you will do is immediately you will go and buy a 16-bit ADC, because for the 16-bit ADC you can get 152 microvolt when you are using 0 to 10 volt. So that is important in the voltage range. So when I am using 0 to 10 volt, see 0 to 10 volt, so that is a voltage range, and then for 16-bit ADC you are going to get a resolution 152 microvolt. When the voltage is different, again this, if 0 to 5, then this will be much lower. In 0 to 5, say this is your interest, your range of interest, then your resolution is 152. So you got an ADC. So 0, so this is first pin, and then second pin, and so on. This is the 16th pin, and then this is your analog, this is your clock. So here your input. So then your interest is sensing 152 microvolt. That much increase is input plus 152 plus or minus 152 microvolt is your interest. You want to vary, you want to sense that much variation. Means where input plus 152 means it is increasing, means your LSB will be changing. You know what I meant? And suppose this will be, so your input equal to 0 volt, then what will happen? 0, all are 0. When your input increase to 153 microvolt, then what will happen? This will become 1, then this will become all 0. You know what I meant? So then you can sense 152 microvolt. But this will not happen if you don't read the data sheet. Your 16-bit, you have to see effective number of bits. So effective number of bits means they will say that effective number of bits may be 14 in the data sheet. That means you can't rely on the LSB side, these two. These two might be jumping. So the pins are there, but then when you connect a signal 153 microvolt, what will happen is ideally it should be 1000, but then what will happen is these two pins will be just jumping alternatively. Means that is not reliable because of the noise. So that's the reason effective number of bits. Then you, in your design, you should take into account effective number of bits. Then you should say that in order to measure 153 microvolt, you may need a higher resolution than 16 bits. So your calculation is should be based on effective number of bits, not based on the resolution they give on the data sheet in the front page. In the front page, they will write 16-bit ADC. Then you will calculate, and it will be, you will be wrong in the sense. I think I told you previously. I used a 16-bit ADC in the past, and the output when I connected it was jumping. LSBs were jumping, so I didn't get 2 raised to 16 minus 1 the resolution. You can calculate the voltage because of the effective number of bits. Then I checked the data sheet. Then I saw effective number of bit they have given was 14.5. I don't know 0.5 where they come from. It's a calculation. So to be honest, I got I think like 13 pins were stable. Remaining pins were just jumping. Then you can improve the design, and then you can get up to effective number of bits. So your calculation should be based on effective number of bits. Then my question is why these errors are coming? Even manufacturer is struggling with it. That's the reason they design it, but then when they make the real device, they have got noises. There are lots of noises associated with ADC and DAC. So which we already discussed some. So this is a binary output, and then this is an analog input. So when your analog input is increasing, what is happening is your ADC will be jumping from 00 to 001, and then when the analog input is increasing, it will stay here this much region, there is no change. Then again it is a step, and then this step is 1 LSB. So this 1 LSB, that's 1 LSB here. So 1 LSB changing only, you are getting a change. Sorry. Oh, sorry here. Yeah. So binary output and then analog input. So in that one, when the analog input is kind of increasing, then what will happen is this is the 1 LSB. Then only it will go to 0,0,0,1, and then again it will stay there. When this much voltage is increasing, again it will go. You get a step response based on the ADC resolution. So 1 LSB, so that is the width of this step. And then ideally it should be going straight like this. The step should be straight. But then sometimes there is a deviation from the straight line. That also can create an error. I will come to that point. So here, for example, if you are using 3-bit, so here this is a 3-bit output, and you can find out for 3-bit what is the 1 LSB. So if your full scale range, is 10 volt, your input is 0 to 10 volt, then you can find out 10 divided by 2 raised to n minus 1. So that is equal to 1.42. Means when your voltage is 1.42, it will go to 0,0,0,0,1. Then when the voltage go to 2 volt, no change. Again it will go to up when 2.84. Again it will go up. Again it will 3, no change. Again 1.42 into 3. Then again it will go. Something like that. And but then see, this is a straight line. This straight line you will never achieve. If you want to get a straight line, you should have infinite number of bits. That's not possible. So all you can do is you can reduce the width of this LSB if your resolution is very high. Like 16-bit ADC, I already discussed. If it is working, if your effective number of bits is 16, your resolution is 152 microvolt. So then this step is 152 microvolt. So that is the step size is decreasing. But then there are so many errors. The one error is, see, that's the reason the ADC will be always having an error of plus or minus half LSB, because that is called a quantization error. So quantization error means here what you are getting is 1 LSB. So here you got 3 volt, for example this volt. So how much is this? This is 1.42 volt, 1.42 volt. So this is 1.42, and then this one is how much? 2.84. And then here, if this voltage plus or minus half LSB, we don't know. That much variation you can't predict. So that is called a quantization error, because that is due to the quantization of the ADC. So that is called a quantization error. That is already present there. That is called a quantization. Plus or minus half LSB is your quantization error. And then resolution versus accuracy. As I said, you have to be careful. Resolution is what you read on the front page, 16-bit or 8-bit. Resolution does not imply accuracy, nor does accuracy imply resolution. Resolution and accuracy are not identical. An ADC may have 16 bits of resolution, but the ADC or the circuit accuracy may be much less than the resolution because of the internal or external error sources. So that is the accuracy is decided by effective number of bits. Well, again we discussed about effective number of bits. Then you might ask, what are the sources of error inherent in data converters? So there are so many errors when you design ADC. Internal to the ADC, gain or scale error, offset error, differential nonlinearity error, missing code, external, reference and supply noise, clocking jitter. So these things, some you can fix it by a better board, but then these things you can't fix it. So when they calculate effective number of bits, they are taking into account only these part. Your effective number of bits may be much less than, so what you get might be much less than the effective number of bits. You bought a 16-bit ADC, effective number of bits they have given on the data sheet is 14. If you design a crap board, your bit will be, you will be adding noise, and then your bit will be 12 bit, because you are again adding these noises. Then we discussed about SQNR, signal to quantization noise ratio. So there are some standard equations. We don't have to derive it. Using that one, we can find out effective number of bits. So effective number of bits for sinusoidal signal, SNR total signal to noise ratio in dB minus 1.78 divided by 6.02. And then for a triangular SNR total dB divided by 6.02, you don't have that 1.78 here for a triangular. Then SNR for sinusoidal is this much, which we already discussed, and for triangular is this much, which is already we discussed. We don't have to derive it. These are the standard equations, and using this one we can calculate actually effective number of bits if you know signal to noise ratio. For example, a 12-bit converter with 68 dB SNDR really a 12-bit converter? Is a 12-bit converter with a 68 dB SNDR really a 12-bit converter? No. So when we calculate as effective number of bits SNDR, so that is already given 68 dB, this you can measure once you have the ADC. The manufacturer will measure this value. How much is this one? SNDR, they can measure it. Then you substitute in the equation, and then minus 1.76 by 6.02, you will get another 11 bits. So that's how effective number of bits is calculated. So the manufacturer will measure it, and then they put in that values into the equation and get the effective number of bits. So that's the reason here they say that 16-bit, an example AD9461, 16-bit 130 megasamples per second, 16-bit. But then when you read here effective number of bits, see effective number of bits is 12.5. If you are operating, see 12.5 if you are operating at 10 megahertz, 12.2 if you are operating at 170 megahertz, if you are operating at 220 megahertz, 11.9. See 16-bit is where they have talking about effective number of bits is only 11.9. This 0.9 you can straight away take away. You are not going, because this is the mathematical calculation, 0.9. So you will get definitely 11 bit. So if you are getting 10 bit, you should be happy. Then my question is, why do you need 16 bit? So that's the reason you have to be careful when you buy a ADC. Sometimes you are increasing the complexity, but then you are not going to get the return. Maybe a 12 bit might be enough. 12 bit might give effective number of bits 10. With 16, you are going to increase only 1 bit. You know what I meant? So that's the reason you should be knowing about these concepts. Otherwise, when you make a design, you can make mistakes, and also you should be scratching your head. Why my ADC output is jumping? In DSO, you might not see that much jumping because you got only 8 bit. 8 bit and your input range is small. You don't have that much, tight noise. Then how other arrays? So when you design the ADC, why the manufacturers are struggling? Because you are using a lot of non-linear components such as transistor, diodes. Then what is happening is there will be offset error. Offset error means when you plot digital output versus analog. This is for ADC. For the DAC, analog output versus digital input, because DAC it is other way around. So usually offset means so this is a straight line, but then your step is like this. It is increasing, and then it is staying here, it is increasing, and then this step is superimposed on this straight line. But then when you design it, what will happen is this step will not start from the 0. There will be an offset. See, your step will be starting from here, like this. So then this much, that is the offset. Offset means your ADC, previously discussed, if it is a 3-bit ADC, and if it is a 10 volt range, from here to here is 1.42 volt. And then when your input is exceeding 1.42, your output will go from 00 to 001 here, see. But in your ADC, even 1.42 or even more than, it will not change it. Why? Because it is got an offset. Then you have to take into account that offset. Means your ADC, 1 LSB equal to maybe say 1 volt. 1 LSB equal to 1 volt, and then 1 volt is 0 to 1 volt means then your output should go from 000 to 0001, an example. But then when you change it to 1 volt, nothing will happen. Maybe when you change it to 2 volt, then you saw 0001. So means you got a 1 volt offset. So that is called offset error. Same with the DAC as well. In DAC also, when you give digital input 0 0 0, when you give 0 0 0 to the DAC input, you may see 1 volt output. Means then your DAC got an offset. So the offset error is defined as the difference between the nominal and actual offset points. For an ADC, the offset point is the mid-step value when the digital output is 0, and for the DAC is the step value when the digital input is equal to 0. See, digital input equal to 0, DAC this point should be here, but then there is an offset. For the ADC, when your analog input equal to 0, see, it is coming here, so that is the offset. So that offset error is there, but then offset error is okay. If your ADC got offset error, you can fix it because you can correct it, because you know that then you need to subtract with 1 volt in your calculation. So I wouldn't be much worried about offset error because you can correct it. But then the point is you should know there is an offset error. So you have to check it. So when you put the DAC, you put it 0 0 0 and check whether you are getting 0 0 0 0. In the ADC, you have to do the same. You have to vary the voltage at DC. ADC, you should be checking with a DC voltage. When you put 0 0 0 0 0 volt, then you see all are zeros. Then if your LSB is equal to exaggerated version, LSB equal to 1 volt, then you have to vary up to 1 volt. Then immediately you cross the 1 volt, it should jump into 0 0 0 0 1. If it is not getting like that, then you should understand there is a offset. So you can find out when you apply a DC voltage. Then gain or scale error. Again, because you got so many components, then there will be gain. Gain error is a deviation of the slope of the line through ADC, A to D converter, ADC or DAC, endpoints at 0 and full scale from the ideal slope. Like offset error, gain error is easily corrected by calibration. See, gain error means this is your binary output for ADC, this is an analog input. So ideal means it should be straight line. See, it should be straight line, but sometimes what will happen is it will be offset this way, or it can offset even this way. You know what I meant? See, the step should be going like superimposed on this straight line. So if you go back, see, this is a straight line, and then your step will be superimposed on this straight line correctly. But then here what is happening is the step is superimposed on a line, but that is not on this straight line, the dotted line. It got offset this much. See, from here to here, this much offset. And then that is called for even DAC. For DAC, this is analog in output and this is a digital code. So instead of straight line here, your step that is not overlapping on this dotted line, that is the correct line, ideal slope, but there will be an offset. That is because of the error in the gain. Because the gain is, see, from here gain is fine, but then here, so here gain is more or less. Because here the gain is correct, but then when it is going up means when your input is increasing, gain is increasing or decreasing? Increasing. Yeah, if the slope is down, then the gain is decreasing. Again, this is not an issue. If the manufacturer says there is a gain error, you can fix it. But then the whole point I am teaching is you should know what is gain error. Somebody might be talking gain error of ADC is this much, then you should know that is a gain error. I know what is gain error. Then also people might sometimes talk about a differential non-linearity error. Again, these terms you will be paying attention when you design a high resolution ADC circuit. Like 8-bit, nobody will pay attention to these things unless there is something goes wrong. 8-bit usually you don't have any much trouble. When you are going to high resolution ADCs, you have to pay attention to these things so that you should know these terms. So differential non-linearity error, so DNL, usually use it, is the difference between the actual step width and the ideal value of 1 LSB. So there is also another trouble. There is a difference in the 1 LSB value. Therefore, if the step width is exactly 1 LSB, then the differential non-linearity error is 0. Means differential non-linearity error means you calculate your LSB. What is 1 LSB? So you got a 16-bit ADC, and then your effective number of bit is 16, say an example, and then you calculated 1 LSB equal to 152 microvolt, and then 1 LSB equal to 152 microvolt, but differential non-linearity error is it will not be 152. Next time it will be 148, 1 LSB, or it will be 150. So there is a change. So that is called a differential non-linearity error. See, I have written here. See, the step is like this. See, but then you can see the step width is decreasing here. Here one LSB is much less. See, here one LSB is a bit slightly bigger. See, the step here is not same. So that is called a differential non-linearity error. So you should know these terms. And otherwise, when you hear these terms, you will be thinking, what is this differential non-linearity error? So that is a differential non-linearity error. These LSB values might be different for different analog inputs. So much variation is not good. If the DNL exceeds 1 LSB, if the differential non-linearity error exceeds 1 LSB, is non-monotonic. This means that magnitude of the output gets smaller for an increase in the magnitude of the output. If the DNL error of minus 1 LSB is there, also a possibility that there can be missing code. Missing code means if your DNL is a big value, then you might miss one code, because if you change it, then the output is not changing because of the error. So that's called a missing code. So differential non-linearity error, when you plot it for the ADC, it will be something like this. When you plot, this is for a 3-bit, because we take 3-bit as an example. So this is analog input. So then see the step size here, different. See, this is because of the differential non-linearity error. And for the DAC also you can see here the step size is different, means the LSB value is different. Then missing code. So sometimes people, they also mention about a missing code in the ADC data sheet. So missing codes are output digital codes that are not produced for an input voltage, usually due to large DNL. So as I said, the differential non-linearity error is, so the missing code and the DNL both are connected. Why? Because, so we got the ADC and then our resolution is 152. So 152 means when we plot it, so this is the digital, and then this is analog, and then this is 152, and then this is so 304, and then here is 304 plus 152, and then here is 304 plus 2 into 152, you know, so and so 152. So ideally it should be like this. Then digital 0000, then here is 001. So then you will be getting a step like this, and then step like this, step like this, step like this. So then see, you can see here 1 LSB, in all case 1 LSB, see 152 microvolt. But then if you got a differential non-linearity error, means maybe after 152 microvolt, what will happen is when you have DNL, it will come here and then it will not stop here. It can go up to here and then it will go up. So that your 1 LSB is now 304 or more than 304. If your DNL is bigger than like this, then means after 152, when 304 comes, there is no change in the output. It will change only when it becomes 304, this plus 152, this bigger value only it will change it. You know what I mean? So that this part you are missing the data. So that is called a missing code. Missing code means your analog signal increased, but your digital part didn't change it. That is because of the large DNL, large differential nonlinearity error. So that is called a missing code. I think that's all important concepts about the errors. So these are the errors that is happening in the ADC. So that's the reason you have the problem with the effective number of bits. So designing an ADC is very difficult, especially high resolution ADCs. Then the whole point in this lecture is so that you know what is happening when people are talking about a missing code. You know what code is missing. Means your analog input is changing by 1 LSB, but then the output is not changing because of the DNL. Then you should know what is differential nonlinearity error. You should know what is gain offset. You should know what is offset, because gain offset, gain error, these things we can be corrected because that is a constant for one ADC. And means when you are designing, you got some offset, don't worry, you can correct it. Gain error, you can correct it if you know how much. And then you should know effective number of bits. So these are the things you should be knowing about the ADC. Then what I will be touching upon is isolation techniques, because isolation techniques also is important. In your DSO, now everybody knows you have got 3 planes: digital plane, analog plane, USB plane, and then you are using necktie to isolate the digital and analog plane. Then you are also using an isolator to isolate your USB plane from the analog plane. So then what you have to understand is, so you are isolating the noise. So isolation techniques are very important. Not only isolating the noise, sometimes you may have to deal with high voltage signals. Then you will be controlling with low voltage signals. Then also you need isolation. So then how will you isolate? So there are isolation techniques. You may be familiar with some of the isolation techniques, but then I will discuss some isolation techniques. So there are 2 types of isolations. One is isolating the DC voltages. There are some cases, like in your case DSO, you are isolating. Even you don't have to use a necktie if you got an isolating power supply. Like your USB and analog, you don't have a necktie, because within the power supply itself, regulator itself, you got isolation. You know what I meant? Maybe I think you forgot about your DSO. I'll show you. So the DSO, you can see we got analog ground, we got digital ground, we got USB ground, and we are using necktie here to isolate the ground so that we can reduce the noise. And then here you are using again necktie to reduce the noise. And then the power supply, we got the regulator. Here you got the analog ground. Then here you can see when you want to isolate this power ground from USB ground, we are not using necktie. Why? Because this regulator itself got isolation both in the supply and the ground. So this is the ideal case. If you got something like this, we don't need this necktie. So if you don't have isolation in the ground, then you need the necktie. So if you don't have isolation in the ground for your regulator, you have to use necktie. If you got isolation, this is here you don't need even necktie, you can use this one. But then the question is, what are the technologies they are using inside this regulator when you want to isolate it? And another thing is, here we are isolating only DC, not the signals. In some cases you may have to isolate the signal itself, and then you can isolate it. There are ICs. So that's what we are going to discuss in the isolation techniques. So in the isolation techniques, again I have written non-examinable, so there is no confusion. So isolation and non-isolation techniques in power supplies. So non-isolating. So non-isolating means we already studied about buck, step down, boost, step up, buck boost. But here you can see ground is shared between input and output, and hence there is no isolation. Means your input voltage is measured with respect to this point and this point. Then you are stepping up or stepping down, but still that is measured with respect to this point and this ground. This both grounds are connected, so that there is no isolation here. But if you want to have isolation, so these are non-isolating. Non-isolating share common ground or V out. There are various different topologies to achieve an increase, decrease and invert voltages. In most applications, limited ratio of input to output voltages are achievable due to load conditions. In non-isolating, isolating may be necessary when connecting devices that cannot share the same ground due to noise. In your case, DSO, analog and digital ground, an example. Means when to use it. The secondary circuit can be visualized as a battery which has no voltage reference to the primary circuit. Transformer ratios can be harnessed to achieve higher voltage conversion ratios. So isolating. So this is an isolating flyback, similar to boost but uses transformer to isolate output. So whenever you have a transformer coupling, transformer isolation or transformer coupling, the advantage is you already got the isolation. Your ground and power supply both are isolated. But then the problem with the transformer is you can't have DC. You should have AC signals. But then definitely switching control circuits are there. If you can make DC pulsed, then you can use the transformer for isolation. But then you have to filter it later. For example, this is your input voltage and then this is the ground. But then you want to isolate this ground and this power supply from this side. Then you are using a transformer. If you don't have the switching circuit, what will happen is the DC voltage will come through the coil. Here you get nothing, because transformer you need to change the magnetic field and it should be, induced EMF should be there. So then that's the reason they introduce the switching voltage. So this one is, this transformer will be switching on and off. Then this DC will be on and off like switching. Then here you are getting a induced field, but then here also it is varying. It's not DC. So that you have got further smoothing circuit here with the capacitor, and then you are getting your DC. Here the advantage is you are stepping up, because number of coils are more in the output. You are stepping up, but the advantage is you are isolating both the grounds and the rail, supply rails. Again, forward push-pull converter. So there are different types of topologies. You don't have to study, but then the advantage of this one is switches current through transformer similar to using transformer with AC, and then power, it can go from 0 to 1 kilowatt. And then this is these type of things are already available in the market. Example of digital isolator. Yeah, so these are when you see these things, these are dealing with only the voltage, DC voltages. But then sometimes what will happen is you may have some signal coming, but then it is coming to some other part of the board, but then you want to isolate this signal and ground from this side. But then you want the signal here, but then you want to isolate the ground. You know what I meant? In that case, you can buy for signal, because these are for the DC. Even for the signal you can buy, see, 5 kilovolt RMS dual channel digital isolator. So you can buy, these things are available, isolators are. Even for the communication circuit you can buy isolators. You can isolate the signal, not only power, DC. So you should know, isolation means mostly you will be talking about only DC part, but then there are some designs requirement. Sometimes you need to isolate the signal itself. You don't want this signal ground mixing with this part of the part, but then you want the same signal through. Then you can use a digital isolator, or if it is analog, then you can use accordingly. So then what are the isolation techniques? Because these are the important. As a system engineer, you should be knowing what is happening inside, how these people are making isolation. Isolation techniques for signals and grounds. So topics: what is isolation? Why isolation needed? Application using isolation. Introduction to various manufacturing techniques: optical isolation or optocouplers, magnetic isolation, capacity isolation. So these are the important isolation techniques. Then comparing isolation solutions, so that you can find out which is the best suitable for your application. So what is isolation? Then when isolation means, people will be talking galvanic isolation. So you might hear this word, whether you have got galvanic isolation, then you should be thinking, what is mean by galvanic? Galvanic means this is a one circuit, then this got a voltage power supply 1, and then this is the circuit, and then this is the ground. This circuit got voltage supply 2, and then again ground 2. So when these two signals, this got a signals, although circuit 1 and circuit 2 exchange signals, no current pass from circuit 1 to circuit 2. See, means no current means no electrons will be going from this to 2, means fully isolated. So that is called galvanic isolation. So that is the top isolation you can get. Galvanic isolation means no current is flowing through, but then you are getting the signal through. So how can you get it? Then that is called galvanic isolation. That is the top level of isolation. That's what we will be discussing. Then why isolation needed? Safety. Sometimes you may have to deal with the kilovolt signal, and then you may be controlling with some other small signals, so you don't want both mixing up. Level translation. Sometimes you may have to translate the voltages. common mode noise rejection, background loops, earth noise, then standards compliance, medical and industrial devices. So if you are going to work in medical devices, there will be lot of isolation, because you don't want patient getting a shock. If you don't know isolation, why I am teaching isolation is because I don't want to die when I go to hospital because of some pain in my muscle. Then you will be designing an equipment without isolation. So then I will die of electric shock. So I don't want to happen that one. So that is the reason non-examinable, but I want to make sure that this is the isolation technique. So all the medical devices, it has multiple safety features, and then they will be using isolation techniques. Mainly you want to isolate from the AC. In the medical devices, you will see they will be using a lot of things to isolate whatever your sensor you are connecting, that is from the main power supply. A lot of isolation techniques. So simultaneous data and power transmission, short circuit protection, then EMI, electromagnetic interference, sometimes that also can happen. So these are the reason we need isolation. Then type of isolators. Optical isolation, photodiode optocouplers, we will come to that one. Phototransistor, capacitor coupled, transformer coupled, electromechanical, reed switches, Hall effect sensors, relays, joint magnetoresistive. So this is an example of a monolithic transformer based isolator. So when you talk about a transformer, you will be thinking of a big transformer. Actually you can make in the chip these days. So you can see monolithically integrated, it's very, very small transformer. You can use the transformer isolation. So common applications, in general isolation is used for power supplies, motor control, data communications and interfacing, digital logic interface circuit, safety and compliance systems. Applications using isolation, see lot of applications. Again you got applications, see it's not ending. So all these applications we use isolation techniques. So first one is optical isolation or optocoupler. An optical isolator contains two basic elements. When you are using an optical isolation technique or an IC, an LED with the transmits lights across an isolation barrier region which is transparent, then a light sensitive sensing element. Then photodiode or transistor, split Darlington transistor, there are different topologies, I will come to that point. So then optical isolation, so this is IC. So when you buy an isolator, so you can buy optocoupler based isolator. In the optocoupler based isolator, what you can do is, see, this can be used for both signal and DC. See, here you got a LED and a phototransistor. So when this LED is on, this phototransistor will receive the light and then it's going to the base part, then you are getting a collector current. See, like this. So you want to isolate this part supply and ground from this part supply and ground. You know what I meant? So this may be one region, maybe your analog side. This may be your digital side. So you want to isolate. Then you can use an isolator, optocoupler. How it works is, here you are giving, so your signal is going like this, and then here this is the DC voltage. And then when this is on, suppose this is a DC voltage. If this is a DC voltage, then what will happen is this may be 5 volt. Then when the 5 volt is connected, this LED will be on. When this LED is on, the light will go, and here there is a photodiode. So this photodiode, it will receive the light and then it will generate a small current, and then that will increase the base current of this one. When the base current is increasing, you will get a big high collector current, and then that collector current is coming as a V out, and then what you will do is you pull up to your positive voltage here, and then this is your ground. See, so only the light is transmitted across, so this part supply and ground is fully isolated from here. So that's how optical isolation works. It's an interesting technique, because the light is going and the photodiode, you are getting the current, and then transistor is amplifying that base current, and then you are getting a collector current. Then you are using a pull up because you need a higher voltage here. So this is how optical isolation works. So this is called optocoupler, phototransistor optocoupler, high current transfer ratio due to transistor gain. So then it can transfer high currents, high load switching capability. So optocoupler input, So typical ways of driving an optos LED. So LEDs you can maybe sometimes here what we have shown is only the LED here, and then we haven't shown the driving circuit, but receiver part is correct. But then sometimes what we'll do is for driving the LED, people might use a transistor. Why we use a transistor here? When you are driving LED, you can directly use a resistor and then put in the required supply. But then why do you need a transistor?